Differential privacy provides a gold standard for protecting users' privacy while enabling statistical analysis and machine learning computations over their data. However, differential privacy can be challenging to explain and challenging for users to understand. In this session, we'll hear from Professors Rachel Cummings and Jessica Hullman about how clearly explaining and visualizing differentially private computations can enhance users' perception and understanding of how their privacy is protected. By ensuring that users understand how they're protected, we can help reassure users that their private data will remain confidential. This understanding can help them increase their trust in the technologies that apply their data to build new AI systems, which will ultimately enable them to achieve more.
Thank you very much for the introduction, and I'm very happy being here virtually. I am Rachel Cummings, and I'm faculty at Columbia University, and I'll be talking today about some joint work with my collaborators, Gabe, Priyanka, Alyssa, and Marianne. We'll be talking about how to improve communication with end users about a relatively new privacy technology known as a differential privacy. And I'll first give you a brief overview of this tool. It was introduced back in 2006 by Dwork, McSherry, and Seaman Smith, and in pictures it looks like this. Imagine that we have a database of people's data, and we plug this into our favorite randomized algorithm, and this will give us a PDF of the outputs of this algorithm instantiated on this particular database. And so you can think of this as being the space of all possible outcomes of the algorithm, and this is measuring how likely is this outcome to be observed. You can then imagine if I were to change one person's data, say that I change Alice into Javier, and I plug this new database that is the same except for one person's data into my same algorithm, I'm going to get out a different curve. And our hope under a differential privacy is that our new curve is going to be not too different from the original curve. And this will be formalized using a bound on the ratio between these two curves everywhere pointwise. And this is a valuable privacy notion. It seems like we're just bounding ratios of some curves, but in fact we're saying, imagine if an adversary observes this particular output and then tries to make inferences about whether this output was caused by either data including Alice, alternatively data including Javier. Well, in this case, the observer couldn't make a strong inference beyond the amount allowed under this bounded ratio. And so now we can say this formally in math, and I'll say this is not a mathematical talk, but it's important to emphasize that there exists a formal, rigorous mathematical underpinning. And so we say formally that an algorithm that maps from a tuple of data into some arbitrary output range R is going to be parameterized epsilon differentially private if it is the case that for all neighboring databases, which are the same except for one person's data, and for all possible things that may be produced as a result of this analysis, I'm going to output this thing with about the same probability under these two neighboring databases. And so we again see that we're having a bound on the ratio of these two probabilities, and the bound is going to be parameterized by this term epsilon, which of course appears in the exponent. And so we can intuitively say we're bounding the maximum amount one person's data can affect the output. But the bound is through a not quite intuitive sense, is we're bounding worst case probabilities of the ratios under worst case changes in data. And so while this is a little bit mathematically complicated and it's not quite clear how to interpret things, both the academic and the industry communities have really viewed this as being a gold standard for privacy protections. If I had longer, it would go into more specifics as to why this is a nice privacy notion, but I will just say in the past 15 or so years, we have both seen a explosion of these algorithmic tools built to satisfy differential privacy as well as provide accurate analysis for a very wide variety of computational tasks. And they're also being deployed in practice across virtually every major technology company, including Microsoft, as well as some government agencies. But that is in fact not the point of this talk. I'm really thinking about, we have this, experts agree it's wonderful, companies are using it, and now I'm asking, how do we communicate to non-experts? And we see things that look like this. And so this is a kind of level of technical detail. I'm not talking about explaining it to researchers or to engineers or to lawyers. I'm really talking about what do we put on our billboards? What do we put on our pop-up that says here's some privacy information, agree or not? What do we put on the billboard or the pop-up? And so in this work, we addressed a few major research questions. Two of them are going to be included in this talk. We have more in the paper, but again, it's a short talk. And so we wanted to ask, how does the way differential privacy is described impact users' privacy expectations against possibly having their information disclosed or leaked? And then also, how does it impact users' willingness to share data? And so to address these questions, we first went out, we gathered a differential privacy descriptions in the wild. And we found that they really coalesced into 6 primary categories. And I'll go through these. In the paper, we enumerate them in more specifics, but these are the 6 main things. And the first one is this paternalistic, no information. Differential privacy is a gold standard. And then you feel very compelled, but you don't quite know what it is. One of them focused on the techniques used to achieve DP, including the kind of injection of randomized statistical noise. Another focused on the type of analyses of user data that were kind of enabled formally through this privacy technique. And a fourth one focused on trust, including its formalization mathematically, which I didn't think people trust, but I guess they do trust math, as well as the organizations using a DP in practice. And the fifth one talked about the type of risk to the user that was reduced through the use of DP tools. And the final one is one you probably don't in fact want to put on a billboard, but was a direct quote out of an academic paper on a differential privacy. And so for each of these, we built a single sentence that kind of captured what we saw happening in practice, and we then used that in a series of research vignettes. And so our first vignette, I'll sort of give an overview. It's that imagine that you work in the banking industry and you're friends with a group of kind of other people who are working in banking companies in your city. One of your friends is a part of a transparency initiative that wants to publish general statistics about pay in the banking industry, and they have asked everyone in their group, including you, to share their salaries and job titles on the initiative's website, using an online web form on the initiative's website. And then we have this additional privacy description. And so we say, to reduce the intrusion into personal privacy, your friend says they will use a tool that's called a differential privacy. And then we inserted one of our 6 different privacy descriptions, as well as a no privacy baseline where there is no additional privacy information. And we included a second vignette asking about people sharing their medical records with a non-profit to see if there was a difference between salary information versus healthcare information. And then we asked them the following survey. It was very brief. And we first asked, would you be willing to share your data? And then we asked, which of the following information disclosures would you expect to be possible for your data based on this privacy description that was provided? And we gave them 6 different possibilities, and we gave them information about kind of what these entail, and these 6 arose out of a prior work as well. And so hack is about a hacker kind of illegally attacking the data. Law enforcement includes kind of law enforcement with a warrant or a subpoena. Organization is the organization collecting data, and so this is either the kind of salary group, or it is medical nonprofit. Analyst is a person working at the organization analyzing data. Graphs include graphs, charts, statistics, and sharing included a third-party sharing. And so we really wanted to find out which of these different descriptions cause people to expect protections against these six. So we saw pretty heterogeneous effects in terms of which of the privacy descriptions affect which privacy expectations. And there wasn't a one single privacy description that really made people feel protected against everything, and there wasn't one single possible disclosure that made people always feel safe under kind of all possible different privacy descriptions. And so this table shows kind of for each of the possible privacy descriptions and for each possible a disclosure, was there a significant effect in terms of people's expectations of improved privacy relative to the kind of a no privacy baseline. And we're talking about the kind of 95% confidence here. And so bolded means that in fact, yes, it was true that if users were given the kind of unsubstantial privacy definition, and they in fact did expect stronger protections against hacks. And so we see there's not one single privacy description that kind of captures it all. Talking about techniques and risk seem to be impactful. Talking about what things enable is kind of less so. We don't really see kind of a one single answer that's really going to solve everything. But it's important as we talk about people having kind of improved expectations, that we think not just about them kind of expecting stronger privacy protections, but in fact it's about them having a correct expectations about the privacy protections they're going to receive. And so in this case, we have to really talk a little bit more precisely about the different privacy models. And so in fact, we have two different core privacy models. One of them is what's called the kind of central model, and this is where there's one single trusted party who's going to collect everyone's data, store it, analyze it, and then they will publish things externally under the constraint of a differential privacy. And so this enables a much more accurate analysis of data, but there also exists a database that can be hacked, subpoenaed, accessed, etc. On the other hand, we have what's known as a kind of local model, and so this is where kind of users are going to add noise locally to their data before they share it. And so this means that the kind of analyst doesn't actually have a database of raw data, but rather they have a database of kind of noisy signals that are roughly correlated with the data. And this, of course, is going to have a kind of larger error because of this noise, but it also means that there kind of isn't a single database that can be attacked, shared, subpoenaed, and so on. And so of course you're going to see different ground truths under these two different models. And I have an asterisk here, which is important, is a kind of a ground truth depends on some of the specifics. And so these are the ground truths for a quote unquote a typical implementation in this under these models, but you might see different ground truths under different specific implementations. And so in this case, true means it's possible, not necessarily that it will happen, but rather it's possible, and false means that it is just information theoretically impossible. And so now if we compare users' expectations to the ground truth, we see this. And so we see on the top we have things under the local model, under our 7 different privacy conditions, which is our 6, plus a baseline. And on the bottom we have the same thing in the central model. And on this x-axis, we have the fraction of answers that were correct about people's expectations of privacy relative to the ground truth. So you will notice under the central model, and so because it's just true false answers, people are roughly random guessing. That's what we get here. Under the local model, we see things even worse than random guessing. And so this immediately tells us future work is needed here because we are not very good yet at providing differential privacy explanations that enable users to have a correct expectations of the privacy they're going to receive. And so this is huge. And we're going to come back to this in a couple slides, but I first want to address research question 2, which is kind of how do these privacy descriptions affect information sharing? And we saw, in fact, none of the privacy descriptions included a significant effect on people's willingness to share. None of them across the board. We did see that users are going to be more likely to share salary data as opposed to their healthcare data, and this kind of intuitively makes sense. But this is also kind of sanity check that in fact they do care about sharing, they just don't care as a result of our privacy descriptions. And so this also tells us more work is going to be needed here. And in the paper, we have some hypotheses as why this might be. But I want to use my last few minutes to kind of talk about some ongoing work. In particular, how do we explain differences between the local versus central model? And so we saw that we have in fact very different implications of privacy in terms of trust and flow models, but if you write them down in math, they're the same. And so we really have to be a little bit more precise about this. And so one possible option is to think about privacy nutrition labels. And we can say in the central model, you can have some things protected and some things not. And the same thing locally. However, there's a couple drawbacks about this. One is that the central model looks very weak. And so we see here, it looks like there's a lot of things that are not being protected, but in fact, in reality, the actual likelihood of these attacks depend on things outside of the privacy guarantee. For example, the kind of likelihood of a hacker doesn't depend on the differential privacy, but rather depends on the security of your storage. And so instead, we're thinking about kind of modeling this as a data flow. And so then you can say there is some data, and under these two different models, some people can see things directly, in some cases it is protected. And we see here that a privacy barrier simply occurs in a different place in these models. And so it's not that the central model fails to provide adequate privacy protections, but rather we're simply placing privacy barriers differently. And so this is very much ongoing work. I hope to have results in a few months. I don't yet, but this is our ongoing work. And I also want to talk about kind of explaining epsilon. And so I mentioned on slide 2, epsilon is a bound on the log with the worst case ratio under 2 different probability distributions. And this is not how people think about their privacy. And the question is, what is a correct object to describe? Because I surely shouldn't say I'm using epsilon equals 0.5 and therefore it's fine, because we can't expect users to really think about this. But they might care about what is the likelihood of my data being leaked and so on. So we have some ongoing work looking at some alternative ways of kind of presenting this. And this is also being done using like a vignette-based surveys. I don't have time to explain it fully, but it's basically asking, there's some like embarrassing information about you and you have to like complete a survey at work, but you don't want your manager to like find out. And so in this case, we're thinking of doing like text-based descriptions of talking about like based on your data, how likely is it for a certain embarrassing thing to like happen. Also possibly combining this with some like visuals. And then also thinking about like providing like kind of like examples of the output. One important thing is that like differential privacy produces noisy answers, and those noisy answers are not always even possible. And so if we're asking how many people at your work responded to a certain thing, negative 3.2 people is not a valid answer. And so we're also interested whether it matters if we like round these into some like valid answer or not. And again, this is like ongoing work, and we're very excited. Hopefully like in a few months we will have answers. Thank you again for your time and your attention, and please of course stay in touch using the like links at the bottom. Thank you again.
Hi, I'm Jessica Hullman, and today I'll be presenting some joint work with collaborators Priyanka Naniakara, Johes Bater, Shi He, and Jenny Rogers. As a researcher in interactive data analysis and visualization, I come to privacy having spent a lot of time thinking about how people use data for statistical inference to draw conclusions about populations in the world. When we want to estimate some phenomena, say the number of people living in a census block or the rate of a disease in a certain demographic, we collect data or samples. But because we cannot perfectly observe these parameter values in the world, we must model and make statements about forms of uncertainty affecting our estimates. For example, we estimate maybe a sample statistic after collecting data like a mean or proportion. Then to estimate uncertainty in the value of this estimate, we rely on what we know about statistical relationships between sample size and error in an idealized perfect knowledge setting where we can take infinite samples and use this to infer limitations of our inferences. As you can probably tell from this diagram, learning from data under uncertainty is a complex process. So my interest in privacy focuses on how we can help people interested in doing inference from data use and understand advances like differential privacy, which can lead to new challenges due to the additional noise and abstraction that they can bring to this process. First, to ground our discussions, let's consider the canonical form of differential privacy, epsilon differential privacy, which bounds the amount of information we can learn about a private record from a released statistic. Specifically, we want to upper bound the ratio of the probabilities that the statistic takes a given value without one person's record versus the probability it takes that value with the record included. And the privacy budget parameter, epsilon, captures how big this difference is allowed to be. Typically, this guarantee is achieved by adding a calibrated amount of noise drawn from a particular type of distribution, for instance, a Laplace distribution centered at 0 for count data. And while we can't predict the specific amount of noise that will be drawn and added under a certain budget, by setting the parameters of the distribution, in this case the scale of the Laplace, which is what epsilon's controlling, we can make sure we never let this difference in probability get too large. One of the great things about differential privacy is that, unlike many techniques for privacy, which require secrecy about the specifics of the mechanism used to achieve privacy, data providers can be transparent about the privacy budget when they release statistics noised under differential privacy. And in theory, this allows data consumers who might want to use the data to learn about the population to account for the added noise when they model the data. But there are also some big challenges that arise in working with differential privacy in practice, especially when data are meant for inference. The most obvious is the question of how to set the privacy budget parameter epsilon. There's no agreed upon guidance for how practitioners should set this value, as it's intended to be a context-dependent choice. And so instead, practitioners have to reason about this trade-off between accuracy or error and privacy risk under uncertainty. To make some of the challenges that arise concrete, let's start by imagining a scenario involving a data curator who works for a hospital. They're an expert in medical research, but they do not have advanced training in privacy. They plan to release a new data set they collected on hypertension in the Chicago area. And to comply with hospital policy, they need to privatize the data before releasing it in a research report. As is often the case, the data do not completely capture the population characteristics. Instead, they represent a sample, which might be subject to systematic or random sampling error. And in this case, let's assume the researcher targeted a random sample, but they have to contend with sampling error. Because the data will ultimately allow other researchers to do inference, the researcher plans to report confidence intervals on population estimates like proportions of people who have hypertension across these different demographic groups. So what might go wrong as the researcher attempts to negotiate the right budget under probabilistic relationships between utility or accuracy and the level of privacy protection? Well, a major challenge is that often a practitioner's knowledge about what might be an acceptable trade-off between accuracy and risk is not in a form that easily translates to the epsilon value that's needed to use a privacy mechanism to achieve differential privacy. For example, the curator's sense of utility of the data for inference may be implicit, hard to verbalize or translate quantitatively, or they might even need to do further consulting with intended users of the data to get their feedback on acceptable accuracy. They also might not have privacy requirements given to them that are congruent with the differential privacy formalism, especially as many organizations are sort of just now starting to consider privacy more seriously for certain data releases. In particular, there's also complexity that arises when it comes to trying to quantify uncertainty in estimates under differential privacy. This is difficult because the privacy budget can be further lost when you're computing uncertainty in your estimates. For example, one commonly preferred way to quantify uncertainty in an estimate is based on non-parametric bootstrapping. So you're resampling the data with replacement many times, you're calculating whatever your statistic is, maybe it's a mean, maybe it's a proportion. And then to quantify uncertainty in that stat, you're reporting the average over all of these samples that you've done and the distribution of the statistic across those samples. However, when you quantify uncertainty in ways like this, you're accessing the data technically many times, and technically this incurs more privacy loss. So using conventional approaches to quantify uncertainty doesn't always work as expected, and practitioners have to be aware of this so that they know how to seek sort of more appropriate methods. Here's a summary of some of these challenges, which inspired my co-authors and I to develop a user interface system to help practitioners apply differential privacy in practice in settings where data is intended for inference. Our goal is to develop an application that could make use of interactive visualization and simulation to make these relationships and sources of error more concrete for end users who have to make these budget choices. We call the tool Visualizing Privacy, or VIP. So the workflow that we targeted was informed by our collaboration with medical researchers at our university's med school, where there was interest in using privacy preservation and releasing health statistics to the public. A data curator who's trusted by the data provider, in this case a hospital, is tasked with applying DP to data releases intended for medical research. VIP, the system we built, sits between the database and the curator and allows the curator to explore different privacy budgets. When they're satisfied with their allocation of budget across queries or stats they want to report, they release those for data consumers who might then go ahead and conduct inference on the data. For example, another medical researcher might combine the new estimates with other geographical data on hypertension to estimate, say, spatial autocorrelation and hypertension rates. So the data curator comes to the interface with a data set and queries they wish to run. Here's the bare bones layout of the interface. We have query panels, which will show estimates for different queries, in this case hypertension, by ethnicity, age, race, and zip code. And we also have a privacy budget use panel in the upper right, where users can set a total privacy budget and distribute it across queries, as well as a disclosure risk panel on the bottom right, where they can monitor how changes to their budget impact risk of de-identification. Once a data set's loaded and a set of queries are provided by the user, they'll see an accuracy panel for each query. So these plots are showing release distributions under a privacy budget allocation as distributions comprised of dots, along with differentially private confidence intervals on the hypothetical release values and traditional confidence intervals on the observed query results. I'll say more about what's represented in this accuracy panel in a moment. First, let's look at the privacy use panel, which is the starting point of interaction. Here, the user can set a total privacy budget, and they can play with different ways of allocating it across a set of queries they've specified by dragging sliders. They can also set query-specific epsilon values independently if they want, or they can use a responsive mode where changing the epsilon for one query increases or decreases the others by equal amounts to preserve the total budget. So adjusting the budget allocated to any query changes the expected release distribution for that query, which is shown as a discretized probability density function. The vertical black line indicates the observed or the unnoised query value, and the red line animates draws from the expected release distribution one at a time to encourage the user to think concretely about how far the released value of the statistic might be from the observed value. The probabilistic animation also allows them to make quick judgments of effect size by noting how frequently one group's red line is further right than the others. This gives an estimate of the probability that one group's statistic is going to be larger than another's. Two confidence intervals are also shown. First, the colored interval shows 50%, 80%, and 95% binomial confidence intervals using a privacy-preserving confidence interval construction method by Ferrando et al. This method uses a bootstrap approach, but one that does not require additional privacy budget since the intervals are calculated as a post-processing step. We also show gray 50%, 80%, and 95% confidence intervals on the unnoised query results. So these represent simply the uncertainty from sampling error. By comparing the width of the colored and the gray intervals, the data curator can immediately see how the noise contributed by the privacy-preserving mechanism increases uncertainty that the data consumers face about what the population parameter value is. There's also an option to turn off the inference mode, which will treat the unnoised query result as the true result and only show the addition of the differential privacy noise. And we can uncheck this option as well to compare effect sizes with differential privacy and sampling error and only under differential privacy to better understand sort of how much blurrier a difference in values is under differential privacy. Finally, on the bottom right, we see a plot that shows the disclosure risk. So we used an attack model proposed by Lee and Clifton here to define disclosure risk as the upper bound on the probability that an attacker correctly guesses whether a certain individual's data is present after seeing the query result. Hovering over points on the line here, which represent total disclosure risk and disclosure risk under different queries, can help the user reason about how much more informative different query results are about individuals. So VIP was really an initial step towards making it easier for practitioners new to differential privacy to reason about privacy budget setting under uncertainty. There's many additional features that could be added to support more sophisticated analyses, some of which I'll talk about in a moment. First, though, I think it's important to ask whether the interactive visualization approach we took here in the interface appears to have any effect on how potential users think about the accuracy risk trade-off under uncertainty. And so to get a sense of this, we recruited 16 people for a user study using convenience sampling with the goal of assembling a sample of people that include data scientists and researchers who had experience analyzing private or sensitive data, but who didn't have a lot of prior exposure to differential privacy in particular. We asked participants to complete a series of tasks with VIP as well as with a baseline interface, which was meant to capture non-graphical ways that many people might currently try to apply differential privacy. So in this case, we had a spreadsheet to which we had added some simple calculations to help people sort of calculate distributions under different budgets. We counterbalanced the order in our within subject study in which participants used each interface across different participants to get balance. And we followed the task portion of the session up with a semi-structured interview to get qualitative feedback on how people felt that these two different interfaces sort of changed their process. So some of the tasks we had participants do consisted of basic probability estimates and comparisons, including reporting probabilities according to the cumulative distribution function, given a query with a specific budget allocated, or comparing the amount of uncertainty with and without the addition of noise from the Laplace. We also had them judge the effect size of comparisons between subgroups for a particular query, which users of such data might naturally do to judge how real or important a difference between groups seems to be. We also asked participants to split a total privacy budget under various constraints. They had to find the smallest budget values that achieved accuracy constraints and split a budget under risk constraints. And both of these tasks were designed to mimic the sort of probabilistic reasoning that one would have to do to effectively use DP and reason about its implications in a real application or a real world setting. So here's a plot of our results split by question type. We're seeing absolute error on the y-axis here, which is in probability units for the CDF and the effect size questions. It's in epsilon units for risk, equalizing accuracy, and budget splitting questions. And it's in multiplicative factor units for the comparing CI question. Across multiple question types, we see less bias and lower variance with VIP compared to using the SMART spreadsheet. This is in particular true of these probability-based questions involving interpreting the CDF and effect size and comparing these different types of confidence intervals. So participants had access with the SMART spreadsheet to all the same distributions, but they struggled to accurately answer these questions, and we think potentially were doing more guessing because they couldn't achieve an answer they were confident in. Participants did similarly, on the other hand, on the risk questions across the board, but they were somewhat less biased in the budget splitting questions with VIP. As I mentioned, we also recorded participants' confidence in their answers to all of these questions, and we found on average that participants were about 2 points more confident on a scale from 1 to 10 when they were making these judgments using VIP or doing these tasks in comparison to the spreadsheet. So there's various ideas that we have for improving VIP and advancing research at what we might call the human differential privacy interface, including working towards more rigorous evaluation frameworks for budget decision-making tools like VIP, and incorporating further ways to help users of a system like VIP make sense of the implications of a given privacy budget. So for instance, we could help people make sense of accuracy loss using sort of familiar metaphors from statistical inference more generally, like, a certain privacy budget is like losing the accuracy you would lose if you reduce the sample size of your data. I want to end my talk today by highlighting some important things we've learned about user expectations around differential privacy that arose as we developed VIP, but which are also echoed in some debates about differential privacy use in the world more broadly. So one idea behind the design of VIP was that seeing a privacy-preserving mechanism applied directly to one's own data can make the implications of accuracy loss more concrete. However, a challenge here is that technically setting the privacy budget conditional on seeing the noised results and the privatized confidence intervals is leakage, similar to how tuning hyperparameters of an ML model on test data would constitute leakage. The privacy loss risk entailed by this leakage is that by knowing how epsilon was distributed across queries, an end user could infer that the queries with higher epsilon allotted to them actually have smaller data values, for instance. So data-dependent decisions about budget directly conflict with the idea of controlling all privacy loss. So first question is, how could we design a user interface tool like VIP to also account for this potential leakage? So one option is to visualize only data agnostic information, so we lose no privacy as a result of data analysis. And some other tools like PSI do this, but this solution is not always satisfying. So many who come from a statistical modeling perspective know that sometimes data-dependent decision-making about what method to apply or how to parameterize something is much more rational than trying to make all of these choices without being familiar with one's data. Another option is to find similar data to make privacy budget choices on, so you aren't contaminating your budget with the target data. But the hard problem here is that if we invest a lot of time in matching the structure, the distributions for the synthetic or the similar data that we're going to use, we're still kind of in a way back to making data-dependent decisions. But we also need sufficient similarity between the surrogate data and the target data for our choice of budget to be realistic or to be useful. And here, there's actually been an ongoing debate about, whether we can set a privacy budget using past data when it comes to the use of differential privacy at the US Census, which I think is an interesting sort of use case for reflecting on some of these bigger challenges with user expectations. So the privacy experts at the census decided to release demonstration data where differential privacy was applied, but this is to past census data in order to get feedback from people interested in census data on what the right accuracy risk trade-off might be. But some of the demographers who are interested in census data pushed back that, looking at past data to think about the implications of accuracy loss is never going to be enough, because it's precisely these small differences between the current data and the past data that they're trying to estimate. So this really gets at why this is such a difficult sort of challenge. It leaves the final option for dealing with this leakage of carefully developing new budget allocation algorithms for the data curator that can account for this leakage or this tuning cost. Here, one could take advantage of expected redundancy in the analysis process in order to save some extra budget, such as by using correlated noise when you're refreshing the interface. But this also can induce even more complexity for practitioners who are already struggling with applying differential privacy in practice. So there's some hard challenges to address here. At a high level, these questions about data-dependent decision-making connect with a larger and very difficult philosophical question that's commonly debated among statisticians and meta-science researchers, which is, to what extent is it feasible or useful to try to specify a data analysis process a priori so that we avoid overfitting? And there's some deep questions about when should we totally synthetically generate data in order to preserve privacy versus when should we use approaches like differential privacy that I think we also need to help practitioners reason with as, privacy experts. Another part of differential privacy that's often taken for granted by privacy researchers, but can be tricky to motivate for end users, is how we choose attack models in implementing differentially private mechanisms and what the assumptions of a particular attack model are. So as we were developing VIP and testing it with users, we observed many questions about what the disclosure risk in the particular attack model we used meant. So for example, upon learning the details of the Lee and Clifton model that we used, some participants in our study expressed disagreement that that model was really the best way to operationalize risk of de-identification. Differential privacy in general is designed to upper bound the risk of de-identification, but some of the users without much background in theoretical computer science found upper bounds less intuitive than thinking about average or expected disclosure risk. So, they can easily misinterpret what an estimated risk level means under a given attack model. However, even if risk was re-expressed as, an average or an expectation, we still need to help practitioners put risk of de-identification in context for their setting. For example, helping them think about who an attacker might be, what information they might have, and what exactly could happen if someone was de-identified. And these are questions that have come up consistently as well in the debates of using differential privacy at the US Census, where many parties who are interested in the data have had trouble imagining why privacy preservation is so important for data like population estimates. These kinds of questions also get at a bigger source of misaligned expectations that users often bring to differential privacy, which is that they often care more about what is likely versus what is simply possible. For example, the use of differential privacy at the US Census, as much use of differential privacy is, was motivated by this idea of a database reconstruction attack that the Bureau conducted, in which they used publicly available tables to infer fully identifying information for a proportion of the population by starting with names and addresses from a proprietary database. The idea that the census had was that since this is theoretically possible, they had to protect against these kind of attacks. However, these kinds of attacks, or the possibility of such an attack, seems to be in direct conflict with how many non-privacy experts prefer to reason about this privacy risk, which is, what's actually likely or what's actually probable in the world. So many have asked questions like, well, how likely is it that an attacker would use census information versus finding other proprietary databases for which they could get exactly the information they need? What about, if they used aggregate level statistics to enable them to make similarly accurate predictions as a database reconstruction attack would about these protected properties? Why is that not protected by differential privacy? And so there's really this source of confusion really about the philosophy behind differential privacy when it comes to what constitutes a risk of de-identification or an attack on privacy. And so here I think it's clear that the privacy research community should invest more in strategic communication with end users of differential privacy and practitioners about, how exactly differential privacy is defining risk of de-identification and how it's different, from other outcomes that we might think of as similarly risky. So to summarize, tools like differential privacy provide a powerful new means for protecting individual privacy by adding noise to data. But for the world to really capitalize on the power of such techniques, we have to help data practitioners understand and use them effectively. And we also have to help end users align their expectations with how differential privacy works. So beyond addressing some of these remaining technical problems related to challenges like data-dependent decisions, we also need more interactive interface tools that can help people build accurate intuitions about critical differential privacy parameters and help them translate their own potentially hard to verbalize domain knowledge about privacy needs or accuracy needs into the differential privacy formalism. In deploying differential privacy in high stakes settings, we also need to invest, I think, a lot more in strategic communication, as I just said, to avoid confusion and even anger on the part of data consumers who feel like, we're taking accuracy away from them when it comes to data resources, that they're using for inference. So I think if we as computer scientists don't invest in better communicating with users how to set expectations and connect their personal knowledge about data utility or privacy when it comes to applying differential privacy in practice, we may lose their trust in our ability as researchers to provide methods that work in practice, not just in theory. So thanks for your attention.